Welcome to the Drones, the Bridge Inspector's newest tool outside of the box presentation. My name is Kevin Lardner and I'll be the moderator for today's session. Let me take a minute to introduce our presenters here first. Ryan Nadaluk currently serves as the Vice President for Stantec's Global Infrastructure Inspection and Asset Management team with more than 100 bridge inspectors across North America. He has more than 23 years of experience in the fields of structural condition inspection, asset management, preventative maintenance, structural design, and project management. Throughout his career, Ryan has performed and managed tens of thousands of inspections on long-span bridges, complex tunnels, hydroelectric dams, water and gas pipelines, as well as tanks, penstocks, towers, buildings, sign structures, and other assets. He has inspected critical infrastructure in 22 U.S. states and internationally throughout Canada, Barbados, and Saudi Arabia, and is currently developing a full network-wide bridge inspection program for the American Samoa government. Ryan has been a SPRAT Level 3 rope access supervisor for over 10 years and has recently led drone research and inspections in multiple Western states. Also presenting is Sam Johnson, Director of UAS Operations at ARE Corporation. Sam oversees the implementation of drone technology across all of ARE's market verticals, including on many of the 3,500 plus railroad bridge inspections performed by the company nationwide. Sam has extensive field experience operating in complex environments, including national parks, DoD, US border, and even underground DOT facilities. In addition to being a commercial drone pilot, Sam holds a private pilot certificate and advanced degrees in mechanical and aerospace engineering. With that, I'm going to turn it over to our presenters and let them take it away from here.
Thank you so much, Kevin. And thank you all for joining Sam and I today. It's a pleasure to present to you. Sam and I decided not to show our video so you can concentrate on our presentation and so you don't have to see our COVID haircuts. But we wanted to share a couple of fun facts with you. As Kevin stated, I've been doing bridge inspections for over 23 years with all sorts of different methods. Traditional methods, mechanical equipment, climbing, confined space methods, and drones are just the newest tool that inspectors are beginning to use that'll help us. One fun fact that we'd like to share is I've been working in Mississippi the last couple of weeks, and last Sunday we got into a little situation where we found a dog on a bridge, and the video has gone quite viral lately. So after the presentation, you can take a look at that. I'll turn it over to Sam. Thank you.
Yeah, thanks, Ryan. Yeah, Sam here. Pleasure to be presenting with everyone today. Fun little story about my intro into the drone industry. Back in college on a Saturday football tailgate morning, I decided that I needed to have a beer koozie travel farther than I was able to throw it. So I did what any aspiring aerospace engineer would do, attached a couple arms, some motors, a battery, a flight controller, and boom, I had invented the flying beer koozie and built my first drone. And fast forward 10 years, the flying beer koozie has not been a commercial success, but luckily people pay me to fly other things on drones. These days it's more along the lines of $250,000 LiDAR sensors and stuff like that. But that's how I got into it.
Thanks, Sam. Yours sounds funner than mine. All right, everybody. Just wanted to go over a quick agenda. We're going to go over some of the research that Stantec has funded over the last couple of years, and some of how we selected some of the bridges. Sam's going to talk about some of the initial lessons learned. We'll talk about capturing digital records to save over time for your assets. We did some basic cost comparisons versus traditional methods and doing inspections with drones. We'll go into some new recent advancements because technology is accelerating quickly, and then we'll wrap it up for y'all. So first of all, Stantec, my team and I, we do about 5,000 routine bridge inspections a year out of our office, and I wanted to figure out how we could save our clients time and money. And so, there's over 600,000 highway bridges in the United States that have to be inspected per the National Bridge Inspection Standards on typically a 24-month basis. And the costs associated with those inspections can be very large. And if you start shutting lanes down and doing traffic control, user costs and impacts from these inspections can also cause a lot of unknown cost. So what I wanted to do is we know that FHWA now will allow the limited use of drones with certain approvals for some certain elements. And we wanted to see which bridges were best suited to using these drones on to save clients money. And so what we decided was we were just going to focus on redundant bridge, super and substructures, where historically mechanical access, underbridge inspection units or this and that would be required. And what we wanted to look at, on the NBI, the National Bridge Inventory, there's mostly concrete and steel bridges. And so we were just going to, kind of do our research on that. We were going to try to use just off-the-shelf technology and sensors. And then we were just going to compare the benefits of all of this, this research to see, what we get. Right now, the Stantec teams, we've been flown bridges with drones in Colorado, Nevada, Arizona, North Dakota, New York, and a couple other locations. So the Colorado DOT and the Nevada DOT, as well as the Arizona DOT, allowed us to fly some of their bridges. First, we started off just in Colorado and Nevada. So here on the left, we have a typical concrete, pre-stressed girder bridge, and then on the right, we just have a typical steel bridge that we would traditionally use snoopers to inspect. Both of these structures are in western Colorado over the Colorado River. And we also picked these bridges here to do studies on because it's in rural airspace, and so there wasn't a lot of flight restrictions, and there was a very limited flight planning that needed to happen there. Now, any information we got out of our work, we have to make sure that we can categorize the correct defects per element level inspections. And so we needed really good sensors and things on the drones that we were using, real high-res cameras. But what we were going to focus on is we were going to focus on the substructure units and the superstructure units, the bearings, the girders, the diaphragms, anything that's up underneath the bridge that mechanical equipment would have had to be used. And we wanted to, compare those costs. We were using high-resolution cameras, anywhere from up to 40 megapixels. The higher resolution, the better. A little fact is, the human eye has about 130 megapixel view versus these high-res cameras, and so we needed to use the highest resolution cameras we could to make sure that it was like representing and recreating the human eye. We also, as well as using these still photos, we were using HD video. We also use sensors, infrared thermography. We didn't do any LiDAR or anything, but what we wanted to do with the high-res videos and the infrared thermography was, use those to put into AI programs, crack detection or defect detection over time. And there's lots of companies that are focusing on that. And do 3D model creation, where it's basically photogrammetry, where you just take a series of photos and you overlap them to make a 3D model of the bridge. And we're not trying to inspect the whole bridge. We still had people out there doing other elements of the bridge. From here, I'll turn it over to Sam.
Thanks, Ryan. So I've personally been doing bridge inspections with drones for about 6 years now. And we started off, when I started off, there was no commercially available aircraft with cameras that were able to look up, which is a pretty crucial part for bridge inspections. So we designed and built our own system, and that's how we got started in the bridge inspection world. But, there's been, over the years, huge advancements in the commercially available aircraft out there, but there still isn't one silver bullet. There's not one platform, in my opinion, that kind of checks all the boxes and does everything you could potentially want in a bridge inspection drone. So you got to look at what the goals are for the inspections. Ryan just listed a few of them, and then extrapolate back, what are your constraints, your physical constraints, and what sensors do you need in order to get the data that you're looking for? And depending on what sensors you need, then that might dictate what aircraft platform you need. So on some of these initial bridges that we looked at, we brought several different aircraft models with us, everything from a small drone like on the left up to something a little bit larger on the right. And basically the difference is the payload capacity. But the systems continue to advance, and I'll talk a little bit more about that at the end here. So when doing a bridge inspection with a drone, there's some things you got to consider. You know, there's legal restrictions. You've got to make sure that you're following all FAA guidelines, as well as considering environmental constraints. You know, these are basically flying computers to in a sense. And while some of them are weatherproof or waterproof, many of them are not, and all of them have max wind restrictions. Things like snow, fog, rain, etc., can not only impact the flight, but the quality of the inspection data as well. So you have to consider that. The flight and camera control, you know, are you going to need one or two operators? How is the video, the live feed coming back down to the operators? Battery life, how much time do you have per flight? Generally, we get about 20 to 40 minutes per flight, which means that you've got to have a clear set plan ahead of time. You don't want to be figuring things out as you're going along. You want to make the most out of your flight time that you have available. And then multiple sensors. Like you said, we flew video, photos, infrared. Are you going to need different aircraft to capture the different types of data? And then the viewing stations. Ryan, maybe you can explain what we're looking at here in the photo.
Yeah, so you know, we were out in Nevada here, and you know, Sam was nice enough to be showing us live feed on the drone from his iPad, but he was trying to take pictures and do video, and so I asked him, "Hey, is there any way we can set up a viewing station, you know, on the fly here?" And he said, "Absolutely. You can just, you know, we can just hard cable into my iPad here, and then you know we can just plug it into a monitor." So we had somebody bring us out a monitor, and it was really great. We put the client in the back seat of our work truck and had the AC on, and had this big old monitor, and we realized that we needed the truck a little darker. So we found some work shirts and jackets and things. We threw it over the windshields and on the windows to make it darker so we could see. And so we had a real-time viewing platform. And so that's one thing we learned. And another thing we learned is these big monitors don't like to work off of just power inverters plugged into the cigarette lighter. So make sure you have, you know, backup small generator with cords and stuff and those hard connections cables. Thanks for letting me jump in, Sam.
Yeah, absolutely. Yeah, so there's, you know, nowadays there's getting more and more advanced viewing options. If you have a strong cell network, there are some platforms that are capable of broadcasting using the cell network to, say, a private YouTube channel where somebody can be viewing it remotely. The last thing that I just want to mention there was the pilot positions, which actually I can talk to here. So you have to consider launch and recovery areas. Where is the crew going to operate from? You know, just because you're sending a drone into a hard to reach area, you still need to have your operators in a safe environment that is clear enough for them to take off and land from. You also need to be able to maintain line of sight. That's one of the FAA Part 107 restrictions, that you need to be able to put your eyes on the drone at all times. So you can't be 2 miles away from the bridge and send the aircraft to do the inspection. Pilot communication is very important. You know, when I first started, you actually needed to have a manned pilot's license. So a lot of us still have those licenses. We've kind of brought manned aviation communication and checklists, et cetera, into our drone operations. And that communication between the pilot who's flying the aircraft and then the sensor operator who's running the cameras is very critical in order to have an efficient inspection. And then you're presumably going out to collect lots of data, you've got to have a plan of how to manage that data. So not just a capture plan of how to go about flying it and capturing the data systematically so that you can follow it and know where the data is on the structure when you're reviewing it, but also just how to store it, transfer it between interested parties, etc.
So when when we started here, we started on this steel bridge, and this is right outside of Glenwood Canyon here. And when we started the project, I wanted my engineers to be looking at the data and then somebody else flying. And Sam and his team did a great, especially with all the sensors. But, you know, in inspecting a steel bridge like this, you have a lot of different things going on here. You can see you have different bottom flange sizes where it flares out. You have bolted diaphragm connections. You have welded stiffener connections. You also have welded connections to the gusset plates of this lower lateral bracing and things. And so we wanted to see how well these drones would do and how good we could zoom into some of these details. You know, with doing defect inspections for the FHWA, you know, you have to be able to see very fine cracks and things in steel and concrete to be able to code it correctly. So what I'm going to show you here is, and this one here was a 22 megapixel camera. Here is, we got the drone up underneath the bridge between the bays. The girders were kind of shallow and the diaphragms were spaced kind of close. So we couldn't get it up in between the bays of the girders really, but we got real close. So here you can see up in the top left, I'm going to show you how good these, once we zoom in on these photographs, how well we can see some of the defects. And here you can see some of the things that we're trying to look at. You're right in the center there, you know, bolted connections, and then you have welded connections as well. So once we zoom in here, you can see that, you know, we can see the welds pretty well, but you have a little bit of dirt that goes in some of the feathered areas of the welds, and some shadowing up top. But, you know, I wasn't comfortable as an engineer to say that, you know, I could perfectly see, you know, some type of crack initiation at the top of the stiffeners. And truthfully, on these simple span bridges, the top of the stiffeners, as you all know, is going to be in compression anyway. We're really concerned about the bottoms, and we couldn't really shoot down in that location. So that was a location we really couldn't get the cameras in to fly really well. And so the steel in a general general inspection, it was doing okay, but obviously for some type of fractional critical inspection, we wouldn't have tried that. The FHWA doesn't allow that. So now here, this is just a standard concrete bridge. Was our next structure we went to, and here we'll, you know, this is a little drone video that shows how we were flying out on site there, and you can see the defects here at this closure pore between these pre-stressed girders. You can see some. You can see some spalling down at the bottom and some delamination. You can see some cracking. You can see efflorescence coming from there. And to properly code concrete per element level inspections, you know, we have to see very fine cracking, you know, to, you know, 0.013 and less, and that's for just traditionally reinforced concrete. Pre-stress even has a more tighter tolerance. But when you zoom in here, you know, this is as good as you're going to see from, you know, the human eye. You know, we can see very fine cracking. The cracking that comes over the top of the deck from the rail down to the soffit there, kind of along the top of the photo. Those cracks are just larger than 0.013, so it actually puts those cracks in condition state 2, you know, per the coding. You know, so that was a great result. You know, we can see some efflorescence and some staining there. You can see some pretty fine map cracking down on the bottom right in the web, top web of the pre-stressed girder. And so we were really happy with the results that we got on the concrete bridges. And so, you know, going from the concrete bridges, we decided, well, we like concrete, so let's start focusing on concrete. So this is where we moved into Nevada and started doing some work here. And so this is actually the Galena Creek Bridge. It's south of Reno, and it's one of the more signature bridges in Nevada. You can see here, that's actually Sam and his co-pilot flying there, and here they're actually flying through the ribs of the arch. We got some really good video on these structures here, or this structure, excuse me. This was the typical method, you know, an underbridge inspection unit. That's an Aspen aerial there with the people in the bucket that are doing visual inspections. And so typically, we have traffic control up there. And so you're putting men and women on the deck in traffic control, which is always dangerous. Then you have wind restrictions on a snooper, just like you have wind restrictions to fly a drone. And the snooper couldn't reach some of the parts up underneath that the DOT wanted to see. But because the arm just couldn't get up underneath the arch as well. And that's where the drone really came in and did wonders to help with our inspections here. Here's some photos. These bridges in Nevada, they don't have a lot of defects on here. So we were really trying here to find some. But once we found some defects, this is a hinge location on one of the approach spans. And what you can see here, if we zoom in, is you can actually see a very fine crack. And that crack is actually less than 0.013. And we were able to see it very clear. Once we identified some of these defects with the drone, we actually sent the snooper back just to make sure and take a different look and measure the cracks so we could get a good idea of what the drones are seeing here. And it really helped. It saved a lot of, it saved some good time and money. So here, and going to a cost comparison, these are this is a 3-span, 200-foot long concrete bridge. You can see that, what we found is that the smaller the bridge, you're not saving much money, and actually you actually might, here we actually proved that it was just a little cheaper to get the drone out in those spans over the water there. You can see the pilots in the photo down on the bottom right. We could look at that span visually, but getting out in the Colorado River there in span 2 and 3 was a little more difficult. And the drone definitely saved money because we didn't have to use traffic control. And you can see from the mechanical equipment costs, snoopers are very expensive per day. And the drone and the pilot, that's really where we got the savings between the two. So it worked really, really well on this structure here. Now I'm going to turn it over to Sam to talk a little bit about digital records.
Yeah. So as you're collecting all of this information, just by the nature of using a drone, you're creating a digital record of the inspection. And we wanted to, this is actually the same bridge, the concrete bridge in Colorado. We wanted to test out some photogrammetry techniques that we commonly use at ARE for more mapping, survey, and construction management type applications to see how it would work for bridge inspections. So basically we flew a predetermined flight plan, semi-autonomous. Some of it was done kind of in the office pre-planned, and the drone flew itself and took pictures. Some of it was done manually. And then we have some computer software that we use to stitch everything together, and we end up with a 3D point cloud, which is a digital twin of the structure. What we found when we did it back on this structure was that it came together. We were able to create the 3D model. This is actually a three-dimensional representation of the structure. You can spin it around and take measurements. We did find that for global geometry type stuff, it was good, but for really accurate measurements and fine detail and defect detection, it really left us wanting more. So we've done some recent projects that I'll talk about a little bit later where we've had much better results, and this technology in particular has come a long way in the last couple of years.
Yeah, when you see some of the further photographs and some of the work and digital records that Sam and his team have collected, you're going to see that this is a digital record from just a year, year and a half ago. And, it's a little, it's not as clear in this and that, but the digital records and the algorithms that they're using now, it looks like a photograph where you're going to see coming up. But be able to use these digital records and spin them in 360 degrees and go up underneath the bridge, it really is a great tool for a bridge inspector and for a client to be able to view these structures here.
So, even if we're not creating the 3D models, we're still creating a digital record. We have metadata that goes along with all of the photos or the video, so we know, the location of the aircraft, the time that we flew it, where the camera was pointed, et cetera, all this stuff that can be used to compare defects over time. more consistently and see, is this crack growing from last year? And all these things lead to more automation. I'll talk about that a little bit more at the end here, but the more automated this process becomes, the more repeatable and reliable the data is. So like Ryan mentioned, we also flew thermal camera. This is at the Galena Creek Bridge. We took both RGB and thermal imagery of the bridge deck. You can see the regular photo on the left and then the thermal photo on the right. We stitched them together. It's a little tricky on bridges that are open to traffic, but there are some techniques we used on this one where we were flying well off to the side of the bridge. We're not flying over the bridge at all during this. And we can, in post-processing, if we have enough photos, basically extract the vehicles from the data and then make it look as though the bridge was empty at the time. So that's what we did here. And like Ryan mentioned, this is basically a brand new bridge. I think it's 8 or 10 years old, something like that. So there were no defects here in this bridge deck. But if there were, if there was some delamination, it might show up in the thermal signature. So on the right, you can see the joint in the deck shows up pretty clearly in the blue because it's much colder than the deck. It's got some airflow coming up through from underneath.
So once we had a couple good flights with our sensors under our belt, we decided to tackle some pretty signature bridges out in the West. And as everyone in Arizona knows, this is the Michael Callahan Pat Tillman Memorial Bridge, sometimes referred to as the Hoover Dam Bypass. This bridge is co-owned by the Arizona DOT and the Nevada DOT, and Nevada DOT is responsible for inspecting it. I've been the lead inspection engineer since 2013 on this structure, and actually our teams are going back out here in January to do another inspection. This bridge here and this inspection takes a lot of effort and a lot of engineers and a lot of coordination between a lot of agencies. You have state police on both sides, and then you also have local police, and then you also have Hoover Dam police. And then you also have, other special agencies out there, Bureau of Rec and things that you have to coordinate with. This bridge takes up to 8 engineers that are SPRAT trained, means they're climbers, and SPRAT is the Society of Professional Rope Access Technicians. And it takes 8 of us out there upwards of 10 days with 11,000 feet of rope to string this bridge up and look at all the components that we need to look at. And so it takes a lot of time. You can see these approach columns that are hundreds of feet high. They're 200-300 feet high, and they're on the, you see 4 sets of them on the right there. That's actually the Nevada side. And then you have the one approach column on the Arizona side on the right. We only wanted to do the approach columns to do this study. We didn't want to do the spandrel columns in the arch because they were associated with the arch, and the client was more happy about that. But when we started doing this work, we have to basically rappel them all. And so here on the left, you can see what it takes. Those are 2 inspection engineers on rope that are doing this. Very labor intensive. It takes a lot of time to set up. Those are about 3 hours per drop. And then on the right here is inspecting these columns with the drones. And it came out really, really good. And so showing here, this is some footage we took from the drone. As I was saying, these are, each one of these to drop, this is one of the longer columns. It takes, about 3 hours to do all the setup and breakdown. But Sam, how long were you saying it was to take to inspect these with the drones?
Yeah, it took us, we did photo and video of every face, and it took us about 10 minutes total per face.
Yeah, so there you go. You have a little bit of data that you have to look at afterwards, photographs and things, but it really sped up the inspection. And so a really quick breakdown of the cost comparison just of the approach column. So just the 4 sets of columns on the right, on the left, and the one column on the right, you know, we saved over $25,000. So we cut the cost in half. And you can see where the really big savings came in was from traffic control and the mechanical equipment. And so we proved to the client and to ourselves that you know, using this technology is a lot safer and a lot cheaper. So it turned out really great. Here, I'm going to turn it over to Sam on some recent technological advancements.
Sure. Yeah. So I was, you know, talking about the 3D digital twin and how when we did originally on that concrete structure, it left us wanting more. So we've done quite a bit more research and testing recently on a new system that we've had some amazing results on. And we just recently deployed it on a project with BNSF where we're doing some engineering work. The bridges, there's I think 15 bridges that all have direct fixation where the rails are directly fixed to the bridge itself, and they're replacing the mounting, the fixation mechanisms. So they need some very, very accurate as-builts and get dimensions on that so that we could design the new fastening system to match up with the mounting locations on the bridge. So this is the system on the right. It's the same aircraft that we flew at Galena Creek, but with a different camera system. So it's a dual camera system, super accurately and precisely mounted on that gimbal. Two 42 megapixel cameras. And then on the left here, you can see this is the 3D result. This looks like a photo, but it's actually a 3D photo mesh that you can spin around and take measurements off of.
Yeah, when Sam first showed me this picture on the left here, I thought it was a picture, and he said, "No, this is a 3D model from the LiDAR," and I was amazed at the accuracy. And remember, this is a point cloud here, so he's going to talk about the accuracy. It has extreme accuracy, and so you can measure everything here and spin it. It's pretty amazing.
Yeah, so with the high resolution cameras, we're able to get about the ground sampling distance is 1 millimeter. So every pixel represents 1 millimeter on the bridge, which means that our relative accuracy when we measure point to point on the 3D model was about 3 millimeters. So this is just showing some ground truthing with some with a ruler laid out, and yep, you can verify that 5 centimeters on the ground is actually 5 centimeters in the model. So this was accurate enough to do the engineering analysis that we were asked to do. So on the left, you can see the current fixation system with the bolts. The center was one of the lines that they had already switched over to the new clip system. And basically we needed to get the bolt pattern on the old system so that they could use it for the shim design for the clips. So we were able to get that center to center location accurate to within 3 millimeters, which met their accuracy requirements. Now, I just want to point out that similar to the bridge inspection work that Ryan talked about at the Hoover Dam bypass, where we were supplementing traditional methods, it's the same thing here. There are some dimensions and top of rail elevations that they need to be more accurate, and so we were supported by a traditional survey team, and in fact we need that survey team in order to generate the high resolution, the high accuracy that we're seeing here. So it's just a different process.
Yeah, and for anyone that has worked with the railroad on a new design or rehab, just reducing even a day or two on site, especially on these main lines, really saves a lot of money in coordination and flagging. And so for them to get this type of accuracy in combination with a little bit of traditional surveying was amazing.
Yeah, so I'll briefly touch on some of the advancements on aircraft systems. This is a new system that we just got. When we were initially flying with Ryan, we had multiple different sensors, multiple different flights. Well, now they've combined multiple sensors into a single payload. So with this particular one, we're getting 22 megapixel photos with a 30 times optical zoom. At the same time, we're getting a wide angle picture for context, and the thermal camera all at the same time. So every time we take a photo, we're getting 3 images. We also have this laser rangefinder, which gives us a really precise distance to the target, so we know exactly how far away we are from the subject. There's also some advanced navigation features, like on the left here, for situational awareness, so that the pilot knows, where in relation to the piers and the bridge structure they are.
Yeah, and this new technology that Sam is showing here, I mean, this is within the last 6 months. So this technology didn't even really exist, or did not exist, this camera on the right here, when we were doing our studies. So we would have to do multiple flights with a thermal camera, and then with the do this still photography and this and that. And so this can all be captured in one flight, and the data captured is just even better.
Yeah, and the automation is becoming more of a real thing. It's in general, bridge inspection is a very manual process, and requires pretty skilled pilots, especially to be getting, the under deck inspection. But there are some advanced features on these new platforms. For instance, this one can record your flight. So if you do a manual inspection, the next time you show up to that location, you can hit go and it will automatically fly the exact same path, point the camera in the exact same position, and take the same photos that you took manually the first time out there. So that just improves the repeatability. There's also some fun features, like for instance, this facade inspection tool could be useful for something like the Hoover Dam Bypass Bridge with very, very tall piers. Basically, you select your area of interest with the white dashed line. It breaks it up into, this one looks like 12 or so photos, and then it automatically zooms into each one of those boxes and takes a photo, and then in real time stitches it together. So essentially you end up with a, say, 250 megapixel image of the entire structure that you can zoom in and maintain that same level of detail. Flight time is improving. This is a new aircraft that we just got here at ARE. It's a gas hybrid electric, so it runs off of high octane gasoline. It's got a generator that provides electricity to the motors, and we're getting over an hour and a half flight time with a 14-pound payload, our LiDAR payload. And if you were, just for reference, if you take the sensor off and you just fly the aircraft frame with the generator, they're claiming up to 5 hours flight time. So it's just allows us to do more per flight.
As bridge inspectors, we do a lot of confined space work in steel boxes and concrete vaults and concrete tubs and things like that. And so, and you're putting a man or a woman, into this confined space that, sometimes has, compromised air, or could have compromised air. And of course it's, it's dark and dusty and dirty. And a lot of times it's very hot and uncomfortable, and you're squeezing through small portals or this or that. And so these new confined space aircrafts are really coming along. They either have, guards around the fans and blades, such as the airless on the left, or they have just collision avoidance systems like the one on the right. Confined space is still difficult with aircraft, because you get different wind currents and things in there that are created by the fans, and so it can stir up a lot of dust and dirt and things like that, and it can it brings the particulates into the air. And so what we've found is then when you start taking photographs in there, the particulates start to mess up the photos, and you don't get as clear as photographs in there. But once we start getting more LiDAR on these types of aircraft, and be able to do these 3D models inside and then stitch them together with photogrammetry, that's really going to help the bridge inspector, especially for concrete structures, to do cracking along post-tension ducts or things like that. So these are really coming along. In conclusion, we've found and we've proved, that drones are a very valuable tool and can save money. I needed to prove to myself, and I needed that drones, were cost effective, and I needed to know in what situations they were cost effective or weren't. And so by doing this research, which was a fully the initial bridges we did was fully funded by Stantec under a research and grant program that Stantec has for the engineers. And so I had to apply for it, and I won. But once I got the information back and with working with Sam and ARE, we had true data that we can go and show our clients that it actually saves money, it saves time, that you can do really clear 3D imaging, and that defect detection really is coming along as the future. Using AI and certain algorithms, you can fly these bridges and you can look at defects and find defects, and you can go and fly them year after year if you've got a spalling location with exposed rebar, or if you have a large obviously cracking or efflorescence that's coming out. You can also it's really great for coding. All the image recognition for bridge coatings is getting better, and the advancements in all the technological equipment and gear is just moving at high speed. Even over the course of us doing this work, the technology was changing. And so at Stantec, that's why we have teamed with ARE for these complex 3D imaging projects, because we want our engineers to do the engineering, and we for these complex structures, and then we want Sam and his team, who are certified pilots, and all they do is fly. Especially in the West here, we have a lot of high winds and things like that, and so you can't just fly tiny little drones around and get really good imagery. You have to fly these big boys around that have these larger payloads. And so for right now, for these larger, more complex jobs, we plan to continue our partnership with ARE, to get the data we need. Some of the smaller flights that we just need to go look at something real quick on a routine girder, we can take one of our pilots that has the smaller drone systems and go out there. But as we've shown, multiple sensors and packages are now available, and they're getting better every day, and combining them into one camera, which is great. And then there's many platforms that can be uploaded into that you can do asset management and long-term data tracking. But the most important thing is, as engineers, especially if we're stamping reports or doing, using this data for a rehabilitation or a new design or something, we have to be comfortable with the results that are provided by this information, because we have to put our stamp and our reputation on the line. And so all in all, it came out to be a great project. We got a lot of the data that we needed. We're going to be doing a lot more flying in the future here, but we really appreciate your time to join us on this presentation. And you can chat with Sam and I after the presentation, either at the Stantec booth or in the social lounge. But we're coming up on the 45 minutes here, but thank you all so much. And Sam, I want to say thank you for joining as a co-presenter. And I'd also like to thank ACEC and Kevin, the moderator of this presentation. Thanks, everybody, and have a great day.
Thanks, Ryan and Sam. Quickly, we do have a couple questions to get some answers from here. So let me shoot them off here. Question one, what are snoopers?
Oh, a snooper is a kind of a bridge inspection name for, it's called an underbridge inspection unit. And an underbridge inspection unit is a machine that has a series of hydraulic booms on it and a bucket at the end. And that machine pulls up, it's a big truck that pulls up on the bridge deck, and the engineers get in the bucket, and then the booms launch them over the sides of the bridge, and then the booms are actually capable of kind of retracting and coming up underneath the bridge. So it's a movable platform that's deployed from the top of the bridge deck to be able to get up underneath of a structure. Good question.
Great. All right. And the last question that we have here, what is your opinion of the usefulness and applicability of thermographic imagery on concrete structures? And also any tips on best weather and times of day to fly to obtain good IR images?
I'd like Sam to jump in here, but basically, we've had really great success. Sam, go ahead, and then I'll add on to your answer.
Yeah. So The best time of day is basically any time where there's been some, changing conditions. So either, a couple hours after sunrise where there's been some time for the sun to heat up the surface, or, after, at night, but that has some legal implications with the FAA. You need a waiver to fly at night. So the easiest thing to do, we've had pretty good luck, late morning, before everything reaches a steady state. That's where you want to have the best thermal differential. Ryan, I don't know if you have anything to add there.
Yeah, in terms of inspection value, if you have a lot of delamination or cracking in the bridge, it really works really well if the conditions are right. Because what you're looking for is obviously a difference in thermal signatures, and so if you have delamination in the deck, there's going to be a pocket of cool air, within that delamination that is going to have a different thermal signature, and so. It works really great. If you go out in the middle of the day, 3 o'clock in the afternoon in the middle of Las Vegas or something, you try to do thermal imaging, it doesn't work well because the structure is just so hot. So you need it to heat up like Sam was saying, and then kind of sit overnight. And then that's when the thermal differences come out pretty good. But for using it to find delaminations and defects, subsurface defects due to cracking, delamination, it works really, really good. But if you have a location that's always cold or always in the dark or something, you might not get great results. So with any type of technology, it's not the end all be all, but it definitely is useful in certain situations.